All right, so yesterday we talked about the Claisen condensation. We said with the Claisen condensation, you can approach it one of two different ways. The first way we saw is where you take one ester and you have it react with itself to form some sort of beta keto ester. And we said that the base you pick has to have the same properties as your leaving group, right? So if you've got ethoxide acting as a leaving group, you want to use ethoxide as your base. And then we covered the mechanism. And then we also said we can combo this, right? Where we have an ester that will react with some sort of enolizable ketone or aldehyde. And in this case, you still get a dicarbonyl compound, but this time it's a beta keto ketone or a 1,3 diketone. And then we saw that this will also do intramolecular cyclizations. This example is just called a Diekmann cyclization. So make sure that you are comfortable doing all of the arrow pushing. What ring sizes are always favored? 5 or 6. We normally don't see anything outside of that range. I did want to throw up a few hints because this always throws people. All right, so when you're doing retrosynthetic planning, there's a handful of groups you should look for. So let's say you've got something that looks like this somewhere in your molecule. What sort of reaction could you use to make that? Would you use an aldol or a Claisen? Claisen. Claisen is when you have the dicarbonyls, right? It's good for 1,3 dicarbonyls. And what I mean by that is this carbonyl is 3 carbons away from the other carbonyl, right? So anytime you see a 1,3 dicarbonyl, you can think, I'm probably going to do this with the Claisen reaction. It's probably going to be some sort of ester involved, which is pretty nice. All right. And then if we look at the next one, a bit different. What reaction would we use to make this? Aldol. So aldol reactions are really good for making beta hydroxyaldehydes or ketones. Right, so in this example, we said that alpha is always 1 carbon away, beta is 2 carbons away. We've got an alcohol coming off the beta position. All right, and then last but not least, we've got this one. I'm going to kind of chop off these ends. This would be an alpha beta unsaturated ketone or aldehyde. How would we make this? Yeah, aldol with heat. Alpha beta unsaturated ketones or aldehydes. Does that make sense? This really helps me a lot when I'm doing synthesis planning, is to first just slow down, not let it intimidate me, and then ask myself which reaction would make the most sense for making this unique functional group. It's really easy with these to get overwhelmed, so I'd encourage you to try to do as many practice problems from the book as possible. Quite often, students will say, this makes perfect sense when you do it in lecture, and then on the exam, I have no idea what's going on. That's when you really got to buckle down and do book problems, because not surprisingly, on exams, I don't have the same problems that we do in class. All right. So now let's move on to another type of reactivity. The next one we're going to look at is alkylation of the alpha position. This one's actually pretty straightforward for the first one. So let's take a look at the overall reaction. So let's say we have cyclohexanone. and we want to add some sort of alkyl group to that alpha position. I'm just going to call this alkyl group R. Does anybody have an idea of how we could accomplish this? Black magic? Shake your fist at it, till it reacts. So first thing we've done in all of this chapter is what? We need to deprotonate the alpha position, right? So we need some sort of base. So I'm just going to write down base. We'll keep it super duper generic. When we do that, we'll get our enolate. Then we want our enolate to react with some sort of carbon in order to alkylate it. We can actually do this using SN2 chemistry. So let's just go over the mechanism really quick. Like we saw, these alpha protons are definitely going to be most acidic because your corresponding product will be resonance stabilized. And normally we'll use a base that's pretty strong, so it'll have a negative charge. So now we've got our enolate floating around. And then in the next reaction, like I said, we're going to do an SN2 reaction. Kick off our leaving group, and we can install some sort of new carbon group there. All right, if this is SN2, what sort of R group can we use? Should it be primary, secondary, tertiary? Yeah, it should be primary or methyl, right? So R should be methyl or primary. And then we want some sort of leaving group. I labeled that as X. It could be a tosylate, it could be a halogen, doesn't really matter. The only halogen that doesn't work is which one? Fluorine. Fluorine is a really crummy leaving group. All right, so this one makes a lot of sense just intuitively, right? Really basic SN2 chemistry. All right, I've got a harder problem. So tricky issue. Let's say we have the following starting material. Under certain circumstances, we can make this enolate. Oh, let me clean this up a bit. Where the negative charge is on the right-hand side. And then we can react this with some sort of alkyl halide. To give us that, right? We said that this actually makes a lot of sense, right? Because we know that this is resonance stabilized, where we can delocalize that negative charge. To look like that. And we know we can do this with some sort of base, so let's just fill in the full mechanism, right? So in this reaction, we're going to grab this alpha proton, form our resonance stabilized intermediate, and then this will react and kick off our leaving group. All right, so that's one option. Or, whoops, we've got another option. So let's draw the other option down here. Same idea. But this time we'll deprotonate off the other side. So we'll grab one of these alpha protons. Same sort of idea where this has resonance stabilization too, so we'll draw both resonance structures. Oops, let me spread this out. And we can have this enolate attack that other R group so that we can actually alkylate the other side. Does that make sense? Because it's no longer symmetric, we could run into either option. All right, So what I want you to do is to talk with your neighbor and decide which of these pathways do you think is more favorable and why. All right, does anybody have a theory for which one they think is more reactive? What's your theory, Ian?
Well, the intermediate with the negative charge is a tertiary carbocation as opposed to a secondary, so that's going to be more stable.
So you're saying the one on top has a negative charge on a tertiary carbon?
Yes.
Versus one on the bottom on the secondary carbon? I'd say that's getting on the right track. One thing I would focus on is rather than the negative charge, look at these alkenes, right? Which alkene is more stable? The top one. All right. So this one has the more stable alkene. In fact, I'll just say more stable enol intermediate. Just 1 second, I'll get to you, John. Which means it has the more stable enol intermediate. Let's just leave it at that. All right, so that one has a more stable intermediate on the top. Did anybody have a competing hypothesis? What do you think?
So the bottom one is less scared to come through.
Okay, so John is pointing out a different argument. He's saying that this proton over here is more accessible, right?
Yeah, but it's all that's right. Protons,
So this proton that I've highlighted in orange is actually easier to access on the top, right? Because it's coming off a secondary carbon versus the proton up here. That's pretty hard to approach, right? To deprotonate it, it's kind of stuck in this tertiary spot. Yep. That's a good question. So Ali's asking, would we get a mixture? That's where I get back to tricky issue. Yes and no. So it depends. All right, so let's take a hypothetical. But first, what was your question?
I was just going to ask if that's the difference between kinetics versus the thermodynamics.
Yeah, so you're asking about kinetics versus thermodynamics. That's what we're going to talk about next. But let's just abstractly say, all right, what about the bottom reaction? Let's say I want to favor formation of this product. Does anybody have an idea for how I can favor that? Yeah. Cold temperatures. So your idea was cold temperature. Because we know that this must be the kinetic product, right? So cold temps favor a kinetic product. I think that's a pretty good idea. Anybody else have another idea? Think about the deprotonation event.
big bulky base.
So for the bottom one, you want a big bulky base?
Yeah.
Why?
Because it's more scared to
Yeah. So if you have a really, really big bulky base, it's going to have a heck of a time grabbing that proton, right? Because it's kind of tucked into that tertiary carbon. So for the bottom one, we could favor this using a big bulky base. All right, so we said we could run the bottom one at cold temperature. We know that would favor the kinetic product, which is what this is. This is our kinetic product. All right, versus the top one, we know that this is going to be our thermodynamic product. All right, so now how can we favor the top one over the bottom one? Okay, heat and a small base. So favored at higher temps and favored with smaller base. All right, the reality is sometimes you get a mixture, but you can favor one being major over the other one, just like we've seen with E2 chemistry, for example. The size of the base matters, right? The base has to get into that site to deprotonate it, so we can actually change the size of the base and favor deprotonation of one site over another site. All right, so let's take a look at an example, because we've just kind of been generic using this hypothetical. So let's write down our example situation. All right, in the first example, our goal was to alkylate the more substituted side. We said that we want a small base. What's a good small base we could use? Hydride, right? That's what we use for E2 elimination reactions. So that works. So we could use NaH at room temp. We know that will favor formation of the more stable enolate, right? Because low temps don't really care too much. Room temp is going to default to your thermodynamic intermediate. All right, and then step 2, we can react this with some sort of alkyl halide. All right, down here, we're going to look at the alternate example where we alkylated the other position. All right, so if we think about the bottom one, what's a good big bulky base? So we use terp-butoxide a lot with E2 chemistry because it was super bulky. We've actually seen some better ones though. So DBU, you wouldn't normally see. LDA was the one we talked about at the start of the chapter. Do you remember that one? So LDA is a really nice, super big bulky base. It is way stronger than terp-butoxide, which is pretty nice in this example. So we use LDA. And then oftentimes you'll see this negative 78 degrees Celsius label. Does anybody know how we get things to negative 78? I mentioned it before. Dry ice and acetone. So dry ice and acetone makes this kind of boiling soup. So if you've ever been to a Halloween party and seen dry ice hucked into, the punch bowl or whatever, it's like that, but with acetone. It's kind of fun. All right, so we do that first, and then step 2, we react this with our alkyl halide. So we can actually get pretty good control over this reactivity for this reaction. Does that make sense? Pretty easy transformation. The big trick is knowing which product you'll get and which base you need to choose. All right, the next ones get a little bit more complicated. The first one we're going to look at is called the Malonic Ester synthesis. And again, I like just showing the overall reaction, and then we'll jump into the mechanism and try to make sense of it. But the cool thing with this is you start out with an alkyl halide, and then eventually through a series of transformations, you can basically get a new group to add on. So if you think about it, we've not only added a carboxylic acid, but we've added an additional carbon in addition to that carboxylic acid carbon. So it's a fancy way of thinking about it, but it makes sense, right? This is the alpha position to the carboxylic acid. So really this is a fancy way of alkylating alpha positions to carboxylic acid. All right. All right, so now let's try to make sense of what's going on with the mechanism. All right, the first thing we're actually going to do is use this other reagent. So it's a diester, right? If we think about the corresponding acid that this ester must have been made from, what is this acid called? Malonic acid. I kind of gave it away with the title of the slide, right? So it's malonic ester, right? So this would be diethyl malonate. So you might see that name thrown around. Do you remember when we talked about all the diacids, the oh my, such good apple pie? This is one of the non-IUPAC named acids. All right, so we've got diethyl malonate. First step in all of this chemistry is deprotonation. What sort of base would I use here? So in this one, it doesn't matter small or big, right? Because we only have one type of alpha proton coming off the middle here. But think back to the Claisen chapter. What would be an appropriate base? Ethoxide, right? We don't want it to do transesterification, so we usually pick a base that'll match the leaving group for our ester. Yep.
Could you have like one that was a better leaving group than whatever was on your ester? Would that also be fine? Because
Yeah, although typically it's just easier to pick the same thing. So the question was, can you pick a base where it's a better leaving group? Usually that's not a good base though. So yeah. All right, so we'll make our enolate of this diester. It's actually pretty easy to make this because this is doubly resonance stabilized. So those alpha protons are unusually acidic. All right, and just like we saw in the previous reaction, we've got our alpha enolate, right? We can now do SN2 chemistry like we saw previously. In fact, let me color code this. So in this next step, we're going to alkylate. Same rules apply, right? So this needs to be a methyl or a primary, R group. All right, and we can now create the alpha alkylation. All right, now the next step is a little bit trickier, and in fact, I'm going to condense it down. But what do you think happens if we treat this with strong acid? What will happen to those esters? Thinking back to last chapter. We're going to kick them off. What functional group will we get out? Carboxylic acid. So going back to last chapter, we saw we can convert esters back to carboxylic acids. I'm not going to do that full mechanism because it's pretty steppy, especially with two of them. So go back and review that if you need help reviewing the arrow pushing. But now we've got the dicarboxylic acid derivative. All right, what I'm going to do is I'm going to actually draw this a little bit differently. So I'm going to flip this around and represent it in a slightly different conformation. Why do you think I'm showing it in this conformation right now? Yeah, we get some H bonding occurring. So we've got an interaction right here. So really, this is the more favorable conformer at equilibrium because we get the six-membered ring where it's H bonded together. All right, the cool thing is what happens when you add heat to this. When you add heat to this, it gets really, really, really unstable. All right, so what ends up happening is this will try to steal that proton. So it's going to form a new bond to that proton, right? But that hydrogen can't have two bonds, so it's going to kick down electrons there, and then it's going to kick down electrons over here. All right? So we've got this weird cyclization occurring due to this intermolecular H bond, right? That carbonyl on that carboxylic acid is in such close proximity, it's basically yanking it away. All right? The weird thing, though, is let's think about this chunk, right? We're breaking this bond right here. We're breaking this bond right there. Both of those are being cut, which means this whole group is being cut off of the molecule. What will that become? Carbon dioxide. Yeah, it's pretty neat though. So it helps push this reaction to completion, that formation of CO2. This really will only work though with the malonic ester. Why won't it work with longer esters? Does anybody know why?
Hydrogen on the alcohol further away from the carbon over.
Yeah, exactly. So Armand was saying this is the only intermediate that allows for that 6-member transition state. That's exactly right. So really we're kind of limited in that regard. Yep.
So the intermediate would be phenol.
Oh yeah, sorry. I'm completely skipping a step. So let's be fair. Sorry about that. Let me clean this up. Who is this guy? He's an amateur up there. All right. And we know that under acidic conditions that the keto form, or in this case the carboxylic acid form, will be favored in solution. So this would be our final product. Does that make sense? Sorry about that. I kind of jumped a step. So this would be a enol to carboxylic acid tautomerization. All right. Does that make sense? So kind of reiterating the initial point here. This is really useful for creating alpha functionalized carboxylic acids. So it's a good way of kind of adding on unique functional groups to that alpha position of a carboxylic acid. All right. We also saw earlier in the chapter the Hell-Volhard-Zielinski reaction, where we can install a bromine on the alpha position of a carboxylic acid. But in many ways, this allows alkylation to occur in one step rather than doing a 2-step alkylation reaction, which is pretty nice. All right. So now let's take a look at the next one. All right, so dye substitution. All right. We're not going to go through the full mechanism on this one. But let's consider the following, right? This is going to be a 4-stepper. So the first one, we need to deprotonate, and we said we always want our base to match our leaving group. All right, second one, we want to alkylate once, right? But we can actually do that again, right? Because we still have additional alpha protons after that initial alkylation. So let's do this one more time. So both of these are coming off the alpha carbon. All right, and then if we think about what will happen if we treat it with acid, what will occur? Yeah, this step we said we'll remove the ethyl groups and change it to a carboxylic acid. All right, we can condense this down into one step though and say acid and heat. What will occur then? We know we're going to lose CO2, right? So oftentimes what I do is I just circle 1/2 and I will say this is lost as CO2. It doesn't really matter which side you pick, right? Because it's symmetric. All right, that means that in the end, we'll have a carboxylic acid that looks like this, where we can actually get 2 different alkyl groups functionalized there. We just have to be careful about the order in which we do things. So we don't want to add the acid and heat until we're confident we've alkylated twice.
Wait, where's that ethyl group from?
So the first step we saw where let's go back up here, this transformation, that's going back to chapter 21 chemistry. So we can convert an ester to a carboxylic acid twice. Yep, good question. All right, does that make sense? All right. Let's do a quiz. Not worth points. All right. Let's say I want to do this. Right? So this is still a carboxylic acid. How do we do this? What's that? Not the same thing, right? Because this isn't alpha functionalized anymore. The R group is attached directly to that carbonyl carbon. Not everybody all at once. Toss in magnesium, make a Grignard reagent, and then what? CO2. And then 3, we need to ensure that the carboxylic acid is protonated. So we've got a bunch of different ways of making carboxylic acids. This is really useful for making a carboxylic acid and 1 extra carbon. The one we just covered is really useful for making a new carboxylic acid with 2 extra carbons, right? So it depends on which route you're looking at. Does that make sense? All right. So now let's take a look at the next one. The next one's kind of a variation on the same idea, so it's a lot of review. This is called Acetoacetic ester synthesis. We'll do the same thing. It's not a real word. All right, so same idea. We'll start out with some sort of alkyl halide as our carbon source. And same sort of thing. It's good for making alpha functionalized methyl ketones. The one thing I will really push on is this really only works well for methyl groups, at least as far as this synthesis is concerned. So we're limited to only having that sort of functionality coming off there. All right, so again, let's take a look at the mechanism. The mechanism starts out looking pretty similar, but this time we only have half of an ester. It doesn't matter if you show the ester on the left or the right. Same idea. We want ethoxide to act as our base. We know that these middle alpha protons are going to be a heck of a lot more acidic than these ones. Why? Resonance. It has more resonance. So we'll grab these before we ever touch those. We'll make our enolate. Same sort of idea. We can now have this react with our alkyl halide, just like we did before, through an SN2 reaction. So I'll just label this as SN2 so we don't forget. And we can alkylate that alpha position. If we wanted, we could continue on and do this again, right? So add more sodium ethoxide, a second alkyl halide, and get on a new R group. So we can stop here. It's up to us, though. Yep.
So, assuming we just had this in solution, though, why wouldn't it just continue on?
So normally when we do this, it's stepwise, right? So you remember that last one where I had 4 separate steps? That means after step 1, we isolate this product. And then we react it with this, we isolate that product, and then we do our next step. So it's not a one-pot reaction.
It twice, though, like all that's in solution, so I'm saying why isn't it just continue on?
So you're asking why can't we do 2 alkylations in one step?
Yeah.
We can only form the enolate with a negative charge. We can never have a 2 negative charge, for example, so that's just not going to occur. Yep.
So once we've ripped off all those, what?
No, Ian, his yawn's super loud. It makes me feel wonderful.
Once we ripped off both those alpha protons, can we then attack the other alpha proton on the right side? Or is it already...
So once you get to this step, then you can reform your enolate, but you can't make a double enolate.
That's not what I'm saying. So if we have 2 functional groups in the middle, now, like we've done it again.
Mm-hmm.
Can we then go in again with ethoxide and attack the alpha codons on the right-hand side.
Oh, I see. So you're saying, I'm just going to write this down. Don't include it in your notes. You're saying hypothetically, if you have this on there, can you then go after these protons?
Yes.
You could, but you would need a much stronger base to get very much enolate to be formed, and typically that's not very desirable anyways. So normally we would stop at functionalizing that interior alpha position.
Okay.
Yeah, good question though. All right, so I'll erase that. Next step, we want to get rid of this ethyl group, make this a carboxylic acid. So we're going to apply acid. Just like we saw before, esters will hydrolyze in the presence of acid to give us this intermediate. But just like we saw before, we can kind of spin this around and get that intermolecular H bond view. So let's do that really quick. So really all I'm doing in this reaction is rotating around that bond. You guys kind of see that? All right, so now we've got this intermolecular H bond between those two groups. Same sort of idea. That H bond is so strong that this really just wants to rip it away. So it's going to steal that proton. However, that proton can't have two bonds. So we're going to kick electrons down there and then electrons over there. And really this only occurs at relatively high temperature, so we need to be careful to show that temperature signal, or delta. And we said that this is our enol that will quickly tautomerize to our ketone. Oops. And then our byproduct in this reaction, as we saw before, is going to be that CO2 gas that will bubble out of solution. Does that make sense? So kind of same idea. Yeah.
So you show the pericyclic reaction in equilibrium.
Mm-hmm.
How much of that, like, which direction would that favor?
So this step right here, this is a conformational equilibrium, meaning that sigma bond can rotate freely in space. But we know that this is the more stable conformer due to the intermolecular H bonding opportunity there. So really it prefers to be in that conformation, which also is beneficial for us because that allows for the transition state to occur more readily for the decarboxylation. Yeah. All right, so let's do a challenge one. I'm not sure if we'll have time to finish it, so this might be a take-home challenge. And then the pod that's due tomorrow is extra credit. Typically with extra credit pods, I don't provide a lot of help, so I want you to practice your arrow pushing. All right, so for this challenge, our first reagent will be sodium ethoxide. So you can probably figure out what that's going to do. Then step 2, we'll have methyl iodide. Then step 3 is going to be acid and heat. And my hint is it's going to form a ring. So see if you can make sense of the arrow pushing for this one. This one gets a little bit more complicated, but I think a lot of you can probably figure this out. So that's where we're going to stop today. Tomorrow when we come back, we'll go over this whole mechanism and then continue on to some more advanced chemistry.